Assalamualaikum warahmatullahi wabarakatuh, and a good day. My name is Nurul binti Abdul Razak, and my title is Characterization and Thermal Behavior of Magnesium Aluminium Layered Double Hydroxide. Okay, this is a major background of the layered double hydroxides development starting from 1842 until 1990, as from the reform declared by Hofstadter, and now is as a filler for the nanocomposite in various applications. We continue with schematic diagram of layered double hydroxide, which contain of cation sheet and an ion as interlayer. Okay, the general formula is divalent, trivalent of cation and an ion. Okay, divalent can be calcium, zinc and magnesium, while trivalent can be aluminium, can be ferrum, can be copper, and an ion can be carbonate, nitrate, sulfate. Okay. This complex structure owned by the layered double hydroxide have high thermal stability. This is studied by Dos Santos in 2020. In my study, I use magnesium as divalence and aluminum as my trivalence. Why? Because these two material is most common material in the earth and most abundant in the earth. At the same time, because of both material have high thermal conductivity, low density, and engineered coefficient of thermal expansion. The problem statement of the study is the thermal behavior is very with the molar ratio, and we know that divalent and trivalent cation must be between 2 to 1 to 4 to 1, because beyond the 4.1 and less than 2 to 1, there is no LDH will perform. So we produce magnesium aluminium layered double hydroxide in this range of molar ratio and study the characterization and the thermal behavior. So the objective of this study is to identify the optimum molar ratio of magnesium to aluminium nitrate layered double hydroxide with the best thermal properties. Okay, for the methodology, we use the co-precipitation method, and the solution of magnesium nitrate hexahydride and the aluminium nitrate nanohydride will be stirred for 6 hours at the room temperature. Then after that, in the meantime, we prepared 1 molar of sodium carbonate and 2 molar of sodium hydroxide. Then after 6 hours, we drop this caustic soda into the metal solutions. Then we stir for 18 hours at 65 degrees C, and we maintain at pH 10. Because the pH will affect the size and shapes, so we maintain at the pH 10. So most probably the form of LDH will produce a most similar shape and size. Then we wash, we centrifuge until there is no nitrate left. Then we dry overnight at 100 degrees C. After that, we're going to study the characteristic and the thermal behavior. First, we need to do SRD, then FTR, TM, TGA, and DSC. Okay, the result for SRD, it shows typical reflection for magnesium aluminium layered double hydroxide. The intensity is decreasing as molar ratio increasing, which means the intensity of 2.2 to 1 is higher, then followed by 3 to 1 and 4 to 1. Okay, this reason because the aluminum content is decreasing. So the reason are there is large difference between aluminum and magnesium ionic ready. Thus, it cause distortion of hydroxide layer network and have some difficulty for the alignment, for the directional alignment. Then we say the crystallinity index. The crystallinity of 2 to 1 is higher with 87%, followed by 3 to 1 with 78, and 4 to 1 is 67. For the spacing, the smallest is 2 to 1, and 3 to 1 is 7.78, and 4 to 1 is 7.8. So it's suggested that the small this spacing, because the direction for the alignment, the horizontal, the orientation, the smallest because it's horizontal in orientation, while the bigger spacing due to vertical orientations. So it also shows the DEM. Okay, the DEM is a platelet light, and the most present element is in here is water, which of 59% of it. Okay, for the FTIR, the broad absorptions at 3466 is a stretching vibration of hydroxide in the puslet layer and the intermolecular water molecule. For 1638, it's a very low intensity, whereas the bending vibration mode of the magnesium aluminum metal layered hydroxide, the interaction between this interlayer with water interactions. So the sharpen is the 1384 is a bending of vibration metal hydroxide sheet and stretching vibration of nitrate interlayer. So at the back there, 839 to 670 is out of plane symmetric deformation mode and anti-symmetric deformation mode of nitrate, while at the 770 to 550 is a lattice vibration metal oxides oxygen bonding, which for example magnesium with the oxygen and aluminum with the oxygen stretching. PDA shows that the structure is a typical hydroxide structure. So at the first stage, we see we name the low temperature decompositions. We have low water and interlayer crystallization of the water. Okay, most probably it was agreed that below 200 is a loss of water. And the second is degradation of OH bonding with magnesium or aluminum, and the beginning of decomposition of interlayer. So here is much more, is 15% weight is lost. Then third stage is because of nitrate and ion decomposition. Okay, here is mostly 34 weight loss. Okay, we must desire that the high crystallinity will have high thermostability. However, this can be explained that which may due to result from the random disorder phenomena scattering induced by the aluminum efficient site. The AC curve shows three curves. First is obviously loss of water. The next curve shows uh, the tight and the stronger bond, thus harder to release the OH from the magnesium and aluminum. This formation of oxide and anion decompose need more heat to break down. This have a good agreement with the SID before this, that 2 to 1 is high crystallinity, so it's need more and more heat to break down them. Okay, for the last curve is because it use same ions, so there is not much change at the heat needed at the third curve. As a conclusion, 2 to 1 molar ratio is the best with the high crystallinity and better bonding stability. my presentation end here. Thank you.